We will now use the law of mass action we derived in the previous video to calculate the bound fraction of enzymes in a system exhibiting cooperativity. In this way, we will derive the Hill function. The blue enzyme is currently part of the free enzyme population E sub F. The 4 binding sites to the left are initially vacant. These sites can become occupied by protein X. During time intervals when 4 copies of protein X are hanging out at the 4 sites, the enzyme can have a convulsion, a conformational change, in which its jaws open up toward the right and its spine compresses toward the left, tightly holding on to the 4 copies of protein X. This enzyme, now indicated in red, is part of the population E sub B of tightly bound enzymes. If we suppose that precisely 4 copies of protein X must simultaneously hang out nearby in order for the enzyme to achieve a tightly bound conformation, meaning if we suppose that this reaction cannot proceed in the presence of only 3 copies, 2 copies, 1 copies, or no copies of protein X, then this system displays cooperative binding. For this course, we use a simplified definition of cooperativity in which a reaction cannot proceed unless precisely a threshold number of proteins is present on an enzyme. The portion of the time rate of change of the bound enzyme population E sub B, owing to this binding reaction, is equal to the product of the rate of change of the number of bound enzymes E sub B with respect to the number of binding reactions R sub B that have accumulated since some reference time, multiplied by the time rate of binding reactions. For each binding reaction, we increase the number of bound enzymes by 1. From the law of mass action, the time rate of binding reactions is a proportionality coefficient K sub bind multiplied against 4 powers of the concentration of X, corresponding to the 4 copies of protein X, multiplied against E sub F. The tightly bound enzyme wriggles and jiggles. Occasionally, the entire complex can distort to the point that it blows apart. The time rate of changing the bound enzyme population E sub B, specifically through this unbinding reaction, is equal to the product of the rate of change of the number of bound enzymes with respect to the number of unbinding reactions R sub U that have proceeded since some reference time, multiplied against the time rate of unbinding reactions. During each unbinding reaction, 1 enzyme is lost from the bound population and moved back to the free population E sub F. The only independent reactant that explicitly enters the time rate of unbinding reactions is the bound enzyme complex. The source of stochastic fluctuations that generate the unbinding reaction is the conformational changes of the protein-enzyme complex, not the stochastic occupation of initially vacant binding sites for protein X. Those sites are not initially vacant, they are initially tightly bound. The total time rate of change of the number of bound enzymes is a sum of the partial rates of change owing to binding and unbinding, which can be copied from above. Consider the steady state, where the total time rate of change of the bound population is 0, where the time rates of binding and unbinding are balanced. Move K sub unbind times E sub B from the right to the left-hand side. Recognize that the free enzyme population is the difference between the total enzyme population E sub tot and the bound enzyme population E sub B. Then move all the terms containing E sub B to the left side of the equation, isolating the term K sub bind times the 4th power of the concentration of X times E sub tot on the right-hand side. Cross-multiply. Relabel the ratio of bound enzyme population E sub B over total enzyme population E sub tot as the bound fraction F sub B. Finally, relabel the ratio of coefficients K sub unbind divided by K sub bind as the 4th power of X sub half. This final expression is called a Hill function with Hill coefficient 4. A free enzyme not tightly bound to proteins can become occupied by 4 proteins and take on a tightly bound conformation. This conformation is not permanent. the proteins and enzyme can blow apart. The bound fraction of the enzyme population is x to the fourth divided by x to the fourth plus x sub half to the fourth. In a more general case, a free enzyme might display n dimples. If n copies of protein are simultaneously hanging out, one at each dimple, the enzyme could have a convulsion and grab onto the proteins, achieving a tightly bound conformation. Again, this conformation is not permanent. This is the corresponding Hill function. The bound fraction of the enzyme population f sub b equals x to the n divided by x to the n plus x sub half to the n. The power n is called the Hill coefficient. At this level of simplification, n is the number of sites on the enzyme that must be simultaneously occupied in order for the enzyme to undergo a conformational change that achieves the tightly bound state. To develop an intuitive understanding, we will plot examples of Hill functions. Consider the simple case where n equals 1. This really isn't called cooperativity. Binding is made possible by the presence of a lone copy of protein X. There are no additional dimples where other copies of protein X can work with or cooperate with the copy of protein X hanging out at the dimple already illustrated. We will plot the bound fraction of enzyme f sub b as a function of the concentration of protein X. When X is much less than x sub half, the x in the denominator is negligible relative to x sub half, so f sub b rises approximately linearly with x. When x is much greater than x sub half, the x sub half in the denominator can be neglected relative to x. F sub b then looks like a ratio of x over x, which is just unity. The bound fraction f sub b cannot increase arbitrarily because no more than the entirety of the enzyme population can be bound. The numerical plot of the Hill function with n equals 1 and x sub half indicated visually resembles, in fact, a smooth interpolation between an initial rate of increase and eventual saturation. This is a generic shape that can be stretched horizontally to fit specific systems quantitatively. If spatial conjunctions of protein X and free enzyme are efficiently converted into tightly bound complexes, the Hill function can saturate quickly. Only a small concentration of protein X is needed for the bound fraction of enzyme f sub b to reach, say, 50%. The critical concentration x sub half pulls toward the left. On the other hand, if spatial coincidences of protein X and free enzyme are inefficiently converted into tightly bound complexes, the Hill function pulls toward the right. A large concentration of protein X is then necessary before f sub b reaches 50%. We just looked at the situation where the Hill coefficient n equaled 1. What about the more complicated situation illustrated here, in which an enzyme can present multiple sites for interacting with protein X? The intuition we just obtained from the situation with n equals 1 will now help us to understand Hill functions for other cases where n is greater than 1. We use magnifying glasses to indicate the top dimple. There are other dimples, but we temporarily neglect them. We are effectively looking at a system in which n equals 1, so we can use a Hill function from the previous slide. For example, we plot this one. Just as before, increasing x increases the fraction of time that a copy of protein X is hanging out in the top dimple highlighted by the magnifying glasses. This increases the frequency of opportunities for the enzyme to take on a tightly bound conformation. Thus, increasing x increases the bound fraction f sub b. The dotted orange segment highlights this initial behavior starting from a bound fraction f sub b equals 0 when x equals 0. An increase in x increases the likelihood that copies of protein X are hanging out at the dimples that we have neglected until now. This increases the efficiency with which the occasional presence of protein X at the top dimple can goad the enzyme into taking on the tightly bound conformation. To the extent that we insist on continuing to guide our intuition using a model with n equals 1, we should at least consider a non-cooperative model with greater binding efficiency. This means a yellow curve that has been pulled to the left, as discussed on the previous slide. We again raise the yellow curve and add connecting dotted orange segments. The shape of any individual yellow curve represents the explicit dependence of the bound fraction f sub b on the concentration of protein X owing directly to interactions at the top dimple. The presentation of the family of yellow curves, stacked one on top of the next, represents how increases in the frequency of interactions between protein X and the dimples neglected by the magnifying glasses increase the efficiency with which interactions at the top dimple trigger acquisition of the enzyme's tightly bound conformation. We anticipate an orange curve that appears more sigmoidal or S-shaped than any of the yellow curves from which it was constructed. In fact, the orange curve we have just anticipated is precisely the plot of the Hill function with Hill coefficient n equals 3. It's plotted here with the Hill function for n equals 1, with x sub half drawn at the same horizontal position for both functions. As the degree of cooperativity n increases, the function takes on an increasingly step-like appearance. The concentration x sub half increasingly takes on the role of a threshold concentration, below which copies of enzyme are generally free, and above which copies of enzyme are generally bound. We just used the law of mass action to show that cooperative binding can be described using Hill functions. In the next video, we show that Hill functions provide an opportunity for bistability.